So we talked about for the last few days, 3 days to be exact. We talked about chemical kinetics, right? And chemical kinetics is leading up to us to doing all these things that have to do with what we call equilibrium. Okay, and so I'm talking about solution equilibrium, chemical equilibrium, acid-base equilibrium, right? All these things that have to do with equilibrium. And the reason why is because up until now, you've always been taught that a reaction goes to completion, right? You have like sodium and you have chloride, you put it together and it makes salt, and all that sodium and all that chloride becomes salt, right? That's what you've been told. Well, we've been lying to you. That's not true, actually. We don't actually have reactions that go to, very rare do you have a reaction that goes complete all the way to completion, right? And so the basis of the next few chapters is describing to you all the situations, which is most of them, where you don't have 100% conversion of the reactants to the products. Okay, so we call that chemical equilibrium. Okay, we call that chemical equilibrium. Chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. In a figure above, the equilibrium is finally reached in the third picture. So what you see here in this picture, right, is a sample of very cold dinitrogen tetroxide, right? Dinitrogen tetroxide. And when it's inside this, when it's very cold right here, right, it's a colorless gas. But as the gas starts to warm up, it starts to convert into nitrogen dioxide, right? Nitrogen dioxide. Okay, and most of the time, and up until now, you've been taught that this conversion happens, right? This reaction happens where di, uh, dinitrogen tetroxide going to nitrogen dioxide is going to go 100%, right? Where you won't have any more of the reactant and you only have products left over, right? But in reality, that's not true. In reality, this reaction will proceed until what we call the equilibrium point is, right? And it's the equilibrium point will have a mixture of both reactants and the products, right? Here we have nitrogen dioxide and dinitrogen tetroxide all mixed together, right? And that's called the equilibrium point. And specifically, the equilibrium point is the point where the rate of reaction, right? And this is why we had to learn about kinetics last week, right? It's specifically when the rate of reaction for reactants turning into products is the same thing as the rate of reaction for the products turning back into reactants. Yes, that is crazy, but it's true, right? Your products, even though you've made products from those reactants already, those reactions are actually reversible. They can go backwards and become reactants again, right? Depending on the conditions. Okay. So this is the biggest thing I want you to know from this equation, or not this equation, but this definition right here. What is chemical equilibrium? It's the point at which the reverse reaction and the forward reaction turn in are the same rate. They're exactly the same rate. And so what that looks like in reality, in real life, is that you'll always have this. You'll get to a point where the concentration, right? If it's a gas, it would be pressure, but if it's a solution, it'd be concentration. The concentration of the reactants will remain constant, and the concentration of the products will remain constant after the equilibrium point, right? Nothing will change. And the reason why that is because the rate of creating the products is the same as the rate of creating the reactants, right? So there won't be any change in the number of moles of products or reactants once you reach equilibrium. Make sense? Right? So let's look at that graphically here. Um, there we go. I was like, why is it not moving? Okay, let's look at it graphically here, right? So this is the graphical representation of what we saw up there in the pictures, okay? And we have nitrogen dioxide, right? And its concentration is going up. And here we have dinitrogen tetroxide, and its concentration is going down, right? And so the reactions are happening, right? And we're making tons of product, right? And then we're losing concentration of the reactants, right? And you just keep on going, and then you get to this point, right, where the concentration of both reactant and the product, right, the reactant and the product stays the same, right? And that's called the equilibrium point, right? That's called the equilibrium point. Okay. There's there's a there's no more nitrogen dioxide being made than there is dinitrogen tetroxide being made, right? And so the concentrations remain constant after the equilibrium point. So if we then look at that based on the rate, right? The rate of making nitrogen dioxide here is steadily increasing, steadily increasing. It's going up pretty fast, right? Whereas the rate at making the or destroying, not destroying, I guess it would be decomposing the dinitrogen tetroxide is going down, right? It's going down, but they go up and go down to a point in which they meet each other, and now the rate is the same. And the rate is the same after what? The equilibrium point, right? Does that make sense so far? Not too crazy, right? Okay. So just remember, a system approaches equilibrium. Both forward and reverse reactions are occurring, okay? Right? So the forward and reverse actions are occurring, right? The forward reaction here, reverse reaction there, they're going towards each other, right? At equilibrium, the forward reaction and reverse reactions proceed at the same rate, right? Which is this point right here. And then once equilibrium is achieved, the amount of each reactant and the amount of each product remains constant, right? And so here's the concentration there and the concentration there of both reactant and product, and it remains constant after equilibrium. Okay, it's basically everything I said on the first slide. Okay, it's everything I said on the first slide. So the thing I want you to notice here is that we have two new K things now, right? Remember what K stands for? Exactly, it stands for the rate constant. Thank you, Mary. It stands for the rate constant, right? And here we have Kf, right? Kf and Kf. So Kf is the rate constant for the forward reaction, okay? The rate constant for the forward reaction. There's also another one called Kr. What do you think that means? Close. It's the rate constant of the reverse reaction, right? So Kf is the rate constant of the forward reaction, and then Kr is the rate constant for the reverse reaction, okay? So your very first question today is this: which of the following is true about chemical equilibrium? Which of the following is true about chemical equilibrium? Dan, you got it right on time for the first question. You do have pants, right? Because we have lab today. It's practical. Yeah, it's practical. So you'll be in there actually in the lab doing stuff. Don't worry, you got 15 minutes after class to go run and get some pants. Well, everybody needs a new pair of, Texas Wesleyan pants. That's not that bad. That's not that bad. I know, like Auburn pants are 70, 80, almost 100. Because they charge an arm and leg for the licensing. All right. We've only got 4 responses so far. How many people do we have here today? I thought Oshana came in just a second ago. Did she leave? I mean, her stuff is here. I think she left. So 10. Wait. Wow. All 12 of you are here today. That's crazy. All 12 are here today. Okay, so we should get 11 responses since Oceana's not here. Which of the following is true about equilibrium? Oceana, do this real quick so I can get you on the rolls, on the attendance. Read it carefully, though. Which of the following is true about equilibrium? Which of the following is true about equilibrium? Did you scan it? Okay, good. Which of the following is true about equilibrium? You didn't see any part of me talking about that, so I don't know if you'll be able to answer that question because that was the last slide, the one while you were gone. Wow, you got it right. All right, the vast majority of you got that question correct. The answer is indeed D, all of the above. Those are all true of chemical equilibrium, right? Those are all true of chemical equilibrium. I'm actually very impressed with Oceana because she missed the entire part I was talking about with it, and you got it right. Yep, that's true. So, but that's true. Technically, you're all right, but you're not all completely right. So people who answered D were completely right, right? So good job there, right? Because in fact, remember these rules about equilibrium, okay? A system at least as a system approaches equilibrium, both the forward and reverse reactions are occurring. That is correct. At equilibrium, the forward reverse reaction at equilibrium, the forward and reverse reactions are proceeding at the same rate, and then that's true too. And once equilibrium is achieved, the amount of reactant and product remains constant. Okay, those are three of the most important parts of this chapter. Okay, you need to remember that. It will help you answer a lot of questions. Okay, so let's talk about then a system in dynamic equilibrium. Okay, products are being made, but reactants are also being made too at the same rate, right? In dynamic equilibrium, which we just said that. We just said that. The total amount of product and the total amount of reactant never changes. It never changes. Okay? It never changes. Because if you think about it, if you have a reaction, right, and you have it in like a closed system, right, inside of a little container, and you're doing this reaction, matter can't be destroyed or created, correct? Right? So once you put those reactants in there and it starts making the reaction, unless you add more stuff to it, the total number of reactants and products will always be what? The same, right? Will always be what? The same. So neither reactant nor product can escape the system, which I just said that because you have a closed system. Okay, you have a closed system. And then the ratio of the concentration always stays constant, right, after equilibrium. Always stays constant after equilibrium. So when we look at equations now, you'll never see them where you just have one arrow. Now they have two arrows, right? You can go the forward reaction, right, where you go with the nitrogen tetroxide becoming the nitrogen dioxide, right? But you can also go backwards, the reverse reaction, right? So from now on, your reactions will all have double arrows, unless you're only talking about one part, one half of it, right? The forward reaction and the reverse reaction. But in general, they'll be like this now, okay, with a double arrow. And since a system at equilibrium, in a system where both the forward and reverse reactions are being carried out, we write the equation with a double arrow now. So remember that, okay? I'll have word problems, for example, where you have to write out the equation. And if you forget that double arrow, you will lose points for that because it's very important to remember that we are now in the point in your chemistry careers, right, where reverse reactions can happen, okay? It's no longer just going one direction anymore. So let's take a closer look at the reaction that is the decomposition of the nitrogen tetroxide gas into nitrogen dioxide gas, right? So you remember this already from the last chapter. We've got the rate, right? But instead of it just being the rate constant, but like before, because before it was just the rate constant, and they were all going to the forward reaction and everything was becoming products, right? Now it's the rate constant with an F on it, which I said before means what? It's just the rate constant of the forward reaction, right? And it looks exactly like it does in the chemical kinetics section, right? It looks exactly like it does in the chemical kinetics section, right? Okay. And so the reverse reaction, though, right? The reverse reaction right here is going to be the NO2 gas becoming the dinitrogen tetroxide gas, right? And you can see here the rate law is Kr instead of Kf for the reverse reaction, right? And just like in the chemical kinetics section, we use the coefficients right? To figure out figure out what our exponents are, right? And since this is the rate equation for the reverse reaction, right? This is the rate equation for the reverse reaction, and it's got an exponent of 2, right? That means what? Yes, second order. Thank you. Thank you. Yes, it means second order. All right. So let's take a closer look here then, right? We then learned just a second ago, though, right? When you reach the point of equilibrium, the rate of the forward reaction is what? Equal to the rate of the reverse reaction, right? That's why there's no more products being made, and that's why there's no more, or let's say there's no more net products being made, and no more net reactants being made, right? So now we know that rate at equilibrium, the rate F, or rate forward, is equal to the rate reverse, okay? And then so that means then we can do this where we say the rate constant, the rate law of the forward reaction is equal to the rate constant of what? I mean the rate law of the what? The reverse reaction, okay? But that's only true when? After equilibrium, right? It's only true after equilibrium, okay? Like I was saying before, we've crossed that point now where it's going to be a lot of math, right? The rest of the semester is going to be mostly math. Okay, so be prepared for that. The first half was conceptual stuff, right? But the second half is going to be mostly math stuff, math and chemistry, right? So we can do this thing now where we do the ratio of the reverse reaction, right? Or the products, right? Basically the products, the ratio of the products divided by, not the ratio of the products, the concentration of the products divided by the concentration of the reactants, right? With the exponent of 2 there because of the stoichiometry, the coefficient that was 2, right? And now we have a ratio of products over what? Reactants, right? Which is equal to the forward reaction constant divided uh, by the reverse reaction constant, right? And that alone in itself is called a constant. Specifically, it's called KEQ, which is called the equilibrium constant, right? The constant we get, the rate constant we get when we're at equilibrium is called the equilibrium constant, okay? It's called the equilibrium constant. So the biggest thing about this, right, the thing that I want everybody to remember is when you're writing out these rate laws for equilibriums, right, and the equilibrium constants, the products will always be above the reactants. Okay, remember that. The products will always be above the reactants. Okay? And then the exponents will always be based on what? The coefficients from the balanced chemical equations. Okay? Those are two important things to remember about writing rate equations. Because you'll see, right, just like we did in chemical kinetics, if you can't write the correct, there we go. If you can't write the correct rate equation, you're not going to be able to solve the problem, right? You won't be able to solve the problem. Okay? All right, next question. Which of the following is true about a system in dynamic equilibrium? Okay, which of the following is true about a system that's in dynamic equilibrium? I really hated math when I was going through school. I was like the worst person at math. But math became more fun when they applied chemistry to it for me. Because otherwise, it's just like, just have numbers, just piddling around with numbers, right? But now I actually have things I can see in my hands and take out on the shelf and put it into things and make things happen with, right? Math is so theoretical, right? But when you apply math to chemistry, you can actually do experiments. You can actually make something happen, okay? All right, which of the following is true about a system in dynamic equilibrium? The products are being made, but the reactants are not being made. Total amount of reactants and products doesn't change, Only the reactant can escape the system, or the ratio of the concentrations is variable. Still waiting on two people. One more person. One more person. One more. One more. Awesome. Awesome. All right. So this is the distribution, the breakdown, right? The vast majority of you got that one correct once again. B is the correct answer. Let's look at why B is the correct answer. Okay? It's not why B is the correct answer. And watch it not be B. I'm kidding. I'm pretty sure it is B. Right? Okay, the first one says products are being made, but reactants are not being made. Why is that false? Exactly. Reactants are being made during the reaction equilibrium. Only the reactant can escape the system. Why is that not false? Why is that false, rather? Right. Nothing can really escape from the system unless you have the system open, and then both things can escape. Right? It's not one or the other. Right? Makes sense? And then this one here, why is this one not true? The ratio of the concentration terms is variable. It's constant, and it's not variable, right? So the only one here, the only answer correct here is the total amount of reactants does not change. Product and reactant does not change. Okay? So we introduced this a little while back, the Haber process, right, where we were making like ammonia for like fertilizer. I think I can't remember exactly what the example I used was, like so long ago. Seems like the first day of the semester was so long ago, and we've covered so much stuff. And I'm sure you have all that in your head right now, right, for the final exam, right? It's gonna be great. Okay. So in the Haber process, we have ammonia, right? And ammonia combines with hydrogen gas, right? I'm sorry, let me say that one more time. Nitrogen gas combines with hydrogen gas, and it becomes ammonia gas, right? And that's called the Haber process. So in this very simple equation right here, we can show you that the equilibrium constant here, right? So Kc stands for equilibrium constant, okay? And specifically, it's the equilibrium constant that's based on concentrations. That's why it's a C, okay? The equilibrium constant depends on the stoichiometry. So just like I said in the last slide, right? The products here, which is ammonia, right? It's always over what? The reactants, correct? Right? And then the exponents that we see on the different concentration units on the different species here, right? Like for the ammonia here, the 2 exponent comes from where? The coefficient that's in front of the 2, right? And then the 3 comes from the 3 that's in front of the coefficient in front of the hydrogen, right? And what's the coefficient for the nitrogen gas? 1, exactly, because the coefficient in front of nitrogen is what? 1, okay? That's the first step to getting a KEQ equation correct, right? When you're trying to do an equilibrium problem, like an equilibrium word problem that I might give you on an exam or assignment or a quiz, right? That will be the first step to getting that thing right, is by having the right equation to use. Okay? So let's take a look at this then. This reversible reaction called the Haber process. What do you start with to reach equilibrium, right? So here, this is going to be the same thing that we saw before with the dinitrogen tetroxide decomposing into the nitrogen dioxide, right? It's going to be the same thing before, but the only difference now is that before you had a decomposition reaction, correct? Now you have a combination reaction, okay? You have a combination reaction. So here again, right, we have concentration, right? We have concentration, and we have then time, of course, right? And if we start with only reactants, right, just this side, that means we take nitrogen gas and we take hydrogen gas and put them together, right? Just those two things. This is what it looks like, right? We have our equilibrium point here. We know that it's our equilibrium point because the concentrations are constant afterwards, right? But notice that as time goes by, the concentration of hydrogen goes down, which makes sense because the hydrogen is doing what? It's getting used up by being combined with the nitrogen gas, right? And so that concentration is going down too, right? It goes down to the point where it reaches a constant concentration, right? And at the same time, ammonia is being made, and the concentration of ammonia is going up, right? All the way to the point where the concentration of ammonia is constant, right? So when all three, the ammonia, the hydrogen gas, and the nitrogen gas, right? When all three reach the point where we have the same concentrations of both, right? We're at the equilibrium point. I mean, both. There's three things there. The same concentration as all three things, right? It's you get the both. You get the equilibrium. So let's do it the other way now. Let's do the reverse reaction. Okay. Here, the reverse reaction is actually going to be ammonia decomposing, right? Ammonia is decomposing to become what? Nitrogen and hydrogen, exactly, right? And so look at this thing here, right? Now we have ammonia's concentration going down, right? But then concentration of hydrogen gas and nitrogen gas is going up. And then at some point, they all reach constant concentration. And that point is what? The equilibrium. But the thing I want you to see about this is that even when you're doing the reverse reaction or the forward reaction, right? Look at this. The concentrations are the same, right? They take different paths to get there, right? One is a breakdown and one is a combination, but in the end, right, the equilibrium concentrations for this reaction are identical, right? The concentrate, I mean, there are no numbers there, but we put the graphs right next to each other so you could see that this was at the same line for hydrogen, right? The ammonia was at the same line right there, right? The orange line, and then nitrogen was at the same line all the way across. So it doesn't matter if you're using the reverse reaction or you're using the forward reaction, okay? It doesn't matter if you're using the forward reaction or the reverse reaction. You'll always end up having the same concentrations that are constant after the equilibrium point. Make sense? Right? Cool stuff, man. Cool stuff. So cool. It's so exciting. All right. So let's just talk about now, I alluded to this before, and this, alluded to how to write an equilibrium constant, okay? How to write an equilibrium constant. So this is the same thing we had before, right? When we had the kinetics problems or the rate law, right? Where little a is the coefficient for big A, little b is the coefficient for big B, little b is the coefficient for big B, right? We have the reversible arrows here because it's, it can go backwards and forwards now. And then, excuse me, little d is the concentration, is the coefficient for big D, and little e is the coefficient for big E. How's that actually a little bit different from the kinetics one? Remember what the kinetics one had in it? Say again? Exactly. Instead of being DE, it had CD. Why do you think they changed it for this? So you don't get confused with KC, right? The little KC right there. Does that make sense? Right? There's already a C in this because it's the equilibrium constant. So constant stands for the C this time. That's why they changed it, right? So you don't get confused. And now the products are D and E instead of C and D. Make sense? So don't get confused that you have like a chemical kinetics problem, right? And you have to do the rate law and have C's in there, right? But then you go over to do a equilibrium problem and you don't have any D's and C's at all, and it's all D's and E's, right? Don't get confused. Make sure you know what kind of problem you're doing, okay? So the equilibrium expression, this entire thing is called the equilibrium expression, right? And it's just like it would be on the chemical kinetics one, right? Where the equilibrium constant is equal to, remember I said this before, and I mean, it's going to be said 5, 6 more times today. It's always going to be the products over what? The reactants, right? And then the little letters, the lowercase letters, which are the coefficients, will act as the exponents for each of the concentrations, right, of the reactants and products. Okay. So interestingly enough, when you're doing this with just regular old solution, right, where you have like, you have like a two solids that you dissolve into liquids and you mix them together and a reaction occurs, that's the kind of thing you would use, right? But if you're mixing two gases together, it's actually written this way, right? Where now the equilibrium constant, right, is actually Kp because that stands for pressure. P stands for pressure, right? Because you can use the pressure of a gas as analogous to, right, the concentration of a solution. Does that make sense? The pressure of a gas is analogous to the concentration of a solution, okay? And so what happens then is that Kp is literally the same thing as this up here. It's still reactants, sorry, products divided by reactants, but instead of doing the big letters D and E, A and B, now it's the partial pressure of D, right, times the partial pressure of E divided by the partial pressure of A times the partial pressure of B, right? And then the lowercase letters still being the exponents, right, from the coefficients. So just remember, right, and some people go back and forth and they use them interchangeably, right? But just remember, if you have a Kp, that's going to be based on pressure. If you have a Kc, that's going to be based on concentration, right? And concentration is always in solution. And then Kp is always going to be two gases, right? Gases mixing together and becoming something else. Okay? I know, a lot of rules, but you'll get it. I mean, I got it, and I'm a dumbass. Excuse me, I'm stupid. So, I get it. I'm gonna have to cut that out, aren't I? Anyway, next question here. What is the equilibrium constant dependent on? What is the equilibrium constant dependent on? This next few stretches here for you guys will be very difficult, and I know it will be because it was very difficult for me when I was going through Gen Chem, but I got through it, and you will too. And I'm all the better for it because now, I'm a chemistry professor. So just think a dumb guy like me was able to get it. You guys can get it. Okay, so we're going to do equilibrium constant now. Got 8 responses, 11 responses, one more response, waiting for that one more response, still waiting for that one more response, still waiting for that one more response. There we go. There it goes. Okay, so let's take a look at this here. It's about half and half. Half the people, more than a little bit more than a majority of the people did get the question correct. The answer is in fact B, but the others picked all three kinds of different things there, right? And this question is in fact B because remember, right? Stoichiometry means the same thing as what? Coefficients, right? It means the same thing as coefficients in front of the equations, right? And when you're writing out the equilibrium equation, right, or the equilibrium expression, right, it really much depends on the coefficients, right, the stoichiometry, right? Otherwise, you wouldn't know what to put there in those exponents, okay? Make sense? I believe there's actually a line in there. See, there it goes. The relative amount of change is based on stoichiometry, right? I knew I wrote it in there somewhere. So that way, when you're going through the notes, you can actually see that it says that there, right? Okay, so let's keep talking about gases and equilibrium, right? It's a little bit more different, a little bit more difficult, rather, to do gas equilibrium because you've got to take into account the properties of gases, right? So we can compare the equilibrium constants based on concentration to one based on pressure, right? So the thing about it is that for gases, you're going to have to use the ideal gas law, which is PV equals nRT, okay? PV equals nRT. Which I told Mary yesterday when she was getting help, and she's like, "What? The ideal gas law? What's that?" What's R? It's the ideal gas constant, right? So that means there's going to be a question on your assignment that requires that, right? And so uh, for the gases, right? For the gases, you have to use PV equals RT, where P is the volume. P is the pressure, V is the volume, N is the number of moles in something. R is the ideal gas constant, right? The ideal gas constant. So a mistake people do a lot when they do the ideal gas constant is they use the wrong units. You need to be able to look at your question and see what units it's asking for and use the correct version of the ideal gas constant, right? That has the right units. Okay. Uh, I lost my train of thought. Okay, and then T here is big T. So what does that mean? Huh? What does T mean when it's a big T? Temperature, yes, not time, temperature. Okay, little t is time, big T is temperature. Okay, so for the most part, I'm pretty sure most of the time when you're doing this equation, the version of the ideal gas constant that you're going to be using for R is the 8.134, I believe. 8.134. Okay, I'm pretty sure that's right. But it also depends, like, again, it's going to depend on what the question's asking you for. Okay, there's multiple versions of the ideal gas constant with uh, there's multiple versions of the ideal gas constant. Should be. Did I say that wrong? I don't usually have the constants memorized. So, Mary, what was it that you used yesterday? Do you know? Okay, listen. Maybe I don't know who's right here, so I'm gonna make sure. You're probably right, but let me make sure. Let me Google it real quick because I don't have the gas constant memorized. Ideal gas constant. You're crazy, Mary. It's it is. It's 8.314. Yes, the one that you should be using the most of, right? The one that you should be using the most of is the ideal gas constant that ends with um, 8 point, not ends with, is 8.314, right? And the reason why is because that the unit for that one is joules, moles, Kelvin, right? The other ones have the wrong units, okay? So make sure that you're using the correct one, 8.314, when they're asking for the ideal gas constant, okay? Say, you'll get problems. You'll have a word problem where you'll have to use this equation, and there's multiple versions of the ideal gas constant based on their units, right? But for this equation right here, for doing it with gas equilibrium, the ideal gas constant that you need to use is 8.314. 314. That's okay. I'm just calculate too, right? You're so close, Mary. You're so close. So close. No, that's exactly what you said. I mean, you could if it was a multiple choice question, and you probably get the answer pretty close, right? But I could be super sneaky and do that too, and put that answer in as a choice. Or it might be It might be one of those open ended questions where you start out with the top and then have like five questions linked to it. Huh? I wouldn't do that to you. I wouldn't do that to you. What class is that? Here? Oh, I wouldn't do that here. Well, it depends because part of organic chemistry is having memorized reactions, right? And so if you have them memorized, it's pretty easy. Huh? Anyway, back to this, okay? We're not talking about organic. You have to make it through here first before you get to organic, okay? I mean, I can always help you with organic too. I want to teach organic chemistry. Anyway, so the ideal gas solve, just remember you're going to use R. Usually something else will be given to you, like you'll get pressure, volume, temperature and you have to find the number of moles, or you'll give like you'll or something like that. But the thing that you're going to say is, oh, but you didn't give me what R was. Well, R is always going to be 8.314. Okay. So for these problems, for the problems that deal with this, and so you got to rearrange a few things here though to make it look like an equilibrium constant, right? Because the chapter in gases is over. We did that in Chem 1, right? So you got to be able to apply the ideal gas law now to chemical equilibrium. And the way we do that is by seeing that when we rearrange things, we can divide both sides by V, right? And then you'll get pressure, okay? And then you'll get uh, the top part, nRT, divided by V, right? And so when you do that, you get N divided by V. And what does that look like to you? What does N divided by V look like to you? It's how you figure out the concentration of something, the number of moles divided by the liters, right? Number of moles divided by liters. So that's how you figure out the concentration of something. It literally says it right here, see? N divided by V is what? Concentration, right? It's concentration. Remember when you have these square brackets, they're concentration. So knowing all that now, okay, we can say that the equilibrium constant for pressure is equal to the regular equilibrium constant using concentration multiplied by what? The ideal gas constant and the temperature to the change in the number of moles. Okay, to the change in the number of moles. And what is the change in the number of moles? Is exactly what it sounds like. It's the number of moles of the gas product minus the number of moles of the gas reactant, right? Because when a reaction is occurring, you're losing one, right? And you're getting more of the other. So there's a change in the number of gas moles of something, right? And that's what the change in N is. That's a change in number of moles. That's number of moles of gas product minus the number of moles of gas reactant. Okay? That's good stuff. It's absolutely good stuff. It's a good time. So let's look at this now. This is it demonstrated right here, right? This is the last slide demonstrated. Okay? As you can see here, the ratio of nitrogen dioxide to the concentration of nitrogen dioxide squared to the concentration of dinitrogen tetroxide remains at a constant temperature, remains constant at this temperature, no matter what the initial concentrations of nitrogen oxide and the dinitrogen tetroxide are, right? Because it's a reversible reaction, right? In experiment 4, right here, we started out where we had no NO2 and we were getting more NO2, right? But over here, we're starting out with with mostly NO2, right? And no N2O4, right? And so it doesn't even matter that one side one experiment we start with more NO2, and the other experiment we start with more N2O4, right? In the end, when you get done with the reaction, you always end up having what? Equilibrium, where the rates are the same and the concentrations remain constant, right? Does that make sense? Okay. So the takeaway message from this is that the equilibrium constant in these gases, right, is constant in these gases, right, remains constant and goes like the same thing regardless of the starting concentration. Okay, does that make sense? Regardless of the starting concentration. Okay. So let's take a look at this with using experimental data. Okay, let's look at this using experimental data here, okay? Again, we have the initial and equilibrium constants of the nitrogen gas, dinitrogen tetroxide gas, and the nitrogen dioxide gas at 100 degrees Celsius, okay? So here in the first two experiments, or first three experiments, we've got no initial concentration right there, right? It's actually 0 of the N2O4, okay? N2O4. And as we go through here, we see that for all three of these, the initial concentration, right? The initial concentration of the NO2, though, is actually increasing here, right? We have 3, 2, we have 3, and 4 here, right? 0.02 molar, 0.03 molar, 0.04 molar, right? And then when you jump over here, the reactant is still, I'm not the reactant, sorry. The equilibrium constant is still the same, right? Pretty much experimentally, right? I mean, this little point, point zero zero two difference here could be experimental error, right? It could be a slight difference in the measurement of the actual pressures of this stuff or the concentrations of this stuff. But you notice that their equilibrium constant stays the same, regardless of what? The starting concentration of NO2, right? Over here, though, we start out with 0.02 concentration of the N2O4 and none of the NO2, right? And again, the equilibrium constant is still the same, right? Pretty much on the same order of magnitude, same level. Notice though that in the middle here, we have the individual equilibrium constants for each of the forward and reverse reactions, right? This one's for NO2, and this one's for, this one's for N2O4, and this one's for NO2, right? They actually are different, right? They actually are different. But in the end, once you figure out the KEQ, right, or the equilibrium constant of the entire system, which is when you have the products over the reactants, right? The ratio of the products over the reactants, you get the same equilibrium constant for all different reactions, all four of those reactions, right? So regardless of what the starting concentration is of the reactants, you will always end up with what? A constant equilibrium constant. That's why they call it an equilibrium constant, right? Or KEQ. Okay? Good stuff. So here's something you should remember, okay? Here's something you should remember, and it's kind of like touching our toes just a tiny bit into the water here of Le Chatelier's principle. My old boss used to say, "Stop dangling your feet in water, just jump into the pool." And what that means is get committed, right? Go all in. Stop just testing things out, right? Well, we're not going to do that just yet with Le Chatelier's principle. We're just going to dangle our feet for just a second. We'll talk more about Le Chatelier's principle next week, right? But when you have a K, right, a constant, equilibrium constant, right, that's greater, that's less than 1, right? Wait. That is the greater sign. There we go. Okay, if you have a equilibrium constant that's greater than 1, the reaction favors the products, right? The products will predominate the equilibrium. If you have one that's less than 1, right, then the reaction favors the reactants, right? And so that predominates the equilibrium. So we can see that here. I don't know why, but I was seeing those alligators like backwards just a second ago. It's really weird. When I was in elementary school and they taught me less than and greater than symbols, it was like alligators and the alligator wants to eat the bigger number type of thing. So, and then there was two of them there, and I'm like, wait a second, are they backwards? I'm confused. Anyway, the point is, this picture here, right, demonstrates that. So here we have a K that's greater than 1, and so the equilibrium lies to the right, where you're getting mostly products. If the equilibrium is less than 1, for some reason I knew that was going to happen. That's why I paused. I had this feeling that some alarm was going to go off. Oh, is that why? It's 1 o'clock? That's probably why. It's my internal clock, right? That's what it was. And then so if the K is less than 1, then the reaction lays to the left, right? So it is very probable that I will give you a question in which I give you some Ks, and you need to tell me whether or not it's going to be mostly reactants or mostly products in that reaction. Okay? Just remember, greater than 1, mostly products. Still equilibrium, but still mostly products. Less than 1, mostly reactants. Okay? Remember that. Oh, dang, I just asked you the question that I said I was going to ask you. When a K is less than 1, the reaction is what? I'm gonna go about 5 more slides, and then we'll stop, and then I'll answer some questions. Huh? No, there shouldn't be. Maybe I wrote the question wrong. Let me read it again. Yeah, I'm sorry. I wrote the question wrong because less than one should be favoring reactants, and it also means that reactants are predominant. Good job, guys. That was a test on you. Good job, guys. That's what happens when I write a. Maybe. We'll see. We'll see. Let's see how everybody answered first, though. Hold on. Let me just see. Hopefully, most everybody answered one or the other. Yes, most everybody answered one or the other. Okay, that's good. It's very smart. Because, well, that's the thing. Like, I might not come down on you about it, right? But if Ms. Dickens comes in and sees that your ankles are showing, she might come down on you. Yeah. Those are nice pants, though. All right. We still have 5 slides to get through. Let's get through these slides, okay? All right. So, the direction of chemical equation and the chemical equation in K, right? The direction of the chemical equation in K. The equilibrium constant of a reaction in the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction, right? So, if you take a gander at this up here, right, we see the, again, forward and reverse reactions, right? But one is actually the forward reaction, which is the N2O4 becoming the NO2, right? NO2, right. And then you also have this one here, which is the reverse reaction, which is the NO2 becoming the N2O4, right? Even though this is the forward reaction and this is the reverse reaction, they are both still reversible, right? They can still go both backwards and forwards. Okay? So, but just be able to identify the fact that these are both, this is the forward reaction from the previous example, and this is the reverse reaction. And so what happens here is that when you put the N over, sorry, when you put the reactants over products here, right, which is reactants over products, the products over reactants here, right, you end up with an equilibrium constant of 0.214, right? But when you put the reactants, the products of reactants here, right, then you get an equilibrium constant of 472, right, at 100 degrees. So the thing to know about this here is that the reverse reaction is the reciprocal equilibrium constant of the forward reaction. Okay, it's always the reciprocal. Okay, it's the reciprocal. So if I tell you to, if I have an equation for you, a chemical equation for you, and I want you to break it up into the forward and reverse reactions, right? I want you to tell me the equilibrium constant for each one. And the one for the reverse reaction should always be what? The reciprocal of the forward reaction. Okay? Which, if you just think to yourself in your mind, it's always products over reactants, you'll always get it right. Okay? So, let's find the new equilibrium constant of each reaction when the reaction is multiplied by a multiplier. So, what you can do actually is you can figure out a new equilibrium constant, right, by adding more stuff, right? By adding more stuff. So, here we have the same reaction, N2O4 gas becoming 2 moles of NO2 gas, right? And what we've done here is that we've doubled the number of moles of N2O4, right? And it becomes 4 moles now of NO2 gas, right? So interestingly here, right, here's the equilibrium constant, right, for the normal one. Here's the one with double the concentration here, right? But notice that the KEQ for the normal is still present there, right? But now, so how do you get rid of exponents in fractions? Just a quick little, algebra review. Well, how do you get rid of those exponents, right? So when you have an exponent at the top and an exponent at the bottom, all you have to do is subtract them. And that's how you get the final number exponent, right? See, that's a good thing I told you. That's one of those things you got to remember, right? Because it's basic algebra, okay? So here we have our equilibrium constant, right? Our equilibrium constant, that's normal, right? 1 mole at 0.212. But when you double the reactants, what happens to the equilibrium constant? It gets squared, right? It gets squared. Crazy stuff. All right. So let's take a look at another one, okay? Let's take a look at another thing here. So you can actually do equilibrium constants where there's more than one equilibrium, right? Say it's a two-step problem, right? A two-step uh, uh, um, two-step reaction. Say it's a two-step reaction, right? So here is the overall general reaction right here. Okay, that's the overall general reaction. Okay, the first step of the reaction is this part where NOBr becomes NO and Br2, and its equilibrium constant here is 0.014, right? And then after that, you can take a Br2 and add it to chlorine, right, to get yourself BrCl, okay? And its equilibrium constant is 7.2, okay, 7.2. So how do you figure out then what the equilibrium constant is for both reactions when it's a two-stepper like that? All you do is you multiply the first one times the second one, and you get the third one, right? And the third one, or the overall one, is 0.1. Make sense? So if you have a multi-step reaction, you can figure out the equilibrium constant for each step, right? It's always products over reactants again, right? So it's products over reactants again. So let me just write it for you here, just in case you forgot how to do that, right? So for this one right here, for the first part of the reaction, right, it's going to be NO concentration there, 2, right, Br, right, all divided by the NO Br, two, right? And then for the other one, it's going to be the BrCl to the 2 divided by, I'm saying it slow because my pen's acting slow for some reason right now, Br2 inside of the brackets, and then Cl2 inside of the brackets, right? So this was K1 equals, and this one down here was K2 equals, right? So you can figure out the equilibrium. So in a problem, what would happen is you'd get like concentrations, right? You would get concentrations, and you plug them into the K1 equation to get the first equilibrium constant. You get more concentrations, right? To plug in here to get K2, right? Which is the second equilibrium constant. And all you do is multiply those two to each other, right? Those two to each other to get the overall, which is the K3 of the entire two-step reaction. Does that make sense? Right? Good stuff. Good stuff. So the last thing we're going to talk about is called homogeneous versus heterogeneous equilibria. Homogeneous equilibria occurs when the reactants and the products are all in the same phase, right? And then heterogeneous equilibria occur when something in the equilibrium is a different phase. Okay. So just a rule to take note of here, right? the value used for the concentration of a pure substance is always 1. Okay? The value used for the concentration of a pure substance is always 1. So let's take a look at an example. Here we have the decomposition of calcium carbonate, right? This is actually a heterogeneous equilibrium because we start out with solid calcium carbonate, it becomes solid calcium oxide, and then CO2 gas, right? CO2 gas. So the result is then we have our equilibrium constant equals the concentration of carbon dioxide, right, inside of this closed system right here. And then what that means then is that the equilibrium constant for pressure is then just the partial pressure of CO2 because it's the only one that's in gas phase, right? It's the only one that's in gas phase. So I wanted you to see what's happening here in this picture, okay? Here we have solid calcium carbonate, right? And it's going through a reaction where it's becoming CO2 and calcium oxide here, right? So here's the CO2 gas that's bouncing around, right? And here's the products being made, the calcium oxide, right? So here there's a large amount of calcium carbonate and a small amount of calcium oxide, right? And the gas pressure of the carbon dioxide is P, right? It's just P. So then we look at this one here. A lot of the calcium carbonate has already been converted over to the calcium oxide, right? So now there's more calcium oxide than there is calcium carbonate, right? What happened to the concentration or the pressure of carbon dioxide then? What happened to the concentration or the pressure of carbon dioxide? Nope. It stays the same. It actually stays the same, right? Does it look the same? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9. There's still 9 molecules on both sides. Yeah. So the point of this is the fact that no matter how much Ca or calcium carbonate or calcium oxide you have, right, the pressure of the heterogeneous equilibrium gas will always stay the same. Does that make sense? Right? It will always stay the same. So you could have a little tiny bit of calcium carbonate and a whole bunch of calcium oxide. It will still be, let's say, 9 is the pressure, right? If you have a whole bunch of the starting material, this calcium carbonate, and just a tiny bit of product, calcium oxide, the pressure is still 9, right? Because I say 9 because that's how many molecules that they've shown drawn in there, right? So that's the point of this. Make sure you know that it stays the same, right? No matter what the concentration is of the solids or how much there is of the solid. So let me ask you this question, right? What happens if I let some of this out, like I pick up the cylinder, right, and let out some of the carbon dioxide? What will happen? Yes, that's true. It will reach equilibrium again, right? What happens to the calcium carbonate then though? Does it increase, decrease, or stay the same? It decreases. Why does it decrease? Did you say decrease? Awesome, awesome. Why does it decrease? Right, you gotta find the carbon from somewhere to make the carbon dioxide to reach equilibrium, right? Does that make sense? So I will ask you a question like this on an exam, right? I'll show you some pictures, and I'll ask you at the very end of it all, what happens to one of the solids if I let out the gas? All right? Everyone understand what's happening there? Good job, Stephanie. You got like 3 of those in a row right. 3 of my oral questions in a row. Awesome. I have no idea. This is your last question for today, and then we'll end the class. Last question for the day. Which of the following is an example of a heterogeneous equilibrium? I only got 8 responses. Still waiting for 4 more. Got 10. 2 more people. Might be a typo. I'll check on that for you. Okay, so the vast majority, everybody got that one. Most of them people got that one right. The answer is definitely A, right? Because if you look at this here, the only one here that has 2 different phases is the gas of calcium carbonate and the gas of carbon dioxide and the solids of calcium oxide and calcium carbonate. I was hoping to trick you, right, by having this one down here without any phases on it to see if anybody would pick that, right? I was hoping to trick you there, right? Right. That's a good point. It's a very good point. All right.